This is review video 35, energy and phase changes. So the first thing you need to know is that phase changes can be defined as endothermic or exothermic, just like reactions can be defined as endothermic or exothermic, and any processes that aren't reactions can be defined as either endo or exo as well. Because all that endo or exo really means is that is energy going in or is energy coming out? And that's not inherent to only reactions. It can be any process that we can look at overall. So with an endo phase change, that means, as we know, that something is absorbing energy. In this case, our molecules are absorbing energy. So their Q value, if we were to measure that, would be a positive value. As those molecules absorb energy, they start to move faster, and as such, they're going to get warmer, which means that if they get warmer over time, they're going to move into a higher energy phase. So moving from a solid to a liquid to a gas, or in some cases, a solid straight to a gas. So our three phase changes that qualify as endothermic would be melting, solid to liquid, evaporation, liquid to gas, and sublimation, solid to gas. Our exothermic phase changes, on the other hand, those happen when molecules are releasing energy overall to their environment, meaning that their Q value, were we to measure it, would be negative. If a molecule is releasing its own energy, that means that it's going to start moving slower, and as such, it's going to get cooler, meaning that that molecule is going to move to a lower energy phase. So gas to liquid, liquid to solid, or gas all the way to solid. So those phase changes are going to be freezing, which is liquid to solid, condensation, gas to liquid, or deposition, which is gas straight to solid. This diagram should not look unfamiliar to you because we have seen it before. This is a phase change diagram, and what a phase change diagram looks at is how much heat energy molecules are absorbing and how the temperature of those molecules are changing. So if we start over here at 0, 0 on our axis, we can see that solid molecules are going to absorb energy over time, and then their temperature is going to slowly increase as they do that. Because our solids, as we know, are just organized really, really nicely next to one another, and they're just vibrating in place. So as they absorb that energy, they're going to vibrate more and more and more until they have enough energy to go through a phase change or melting. And this first area right here, if we're moving to the right, represents melting. But you'll notice that during that phase change, our temperature does not actually change at all, despite the fact that those molecules are still absorbing heat energy, because we're still moving toward the right on that axis. And the reason that temperature doesn't change during a phase change is because when we're absorbing energy as molecules, during a phase change, that energy is used to overcome the attractive forces between those molecules. Because remember, when we do a phase change like melting, any attractive forces between the molecules, they break, and these molecules start to move away from one another a little bit. So again, that energy that's being absorbed is being used rather than causing an increase in temperature. So we've got that phase change, and then once the molecules are free of one another, they're just kind of cruising around near each other. They're still a little bit attractive, but not really. Then we start absorbing some more energy, and we start increasing in temperature again until we absorb enough energy to go through our second phase change, vaporization. Again, any of those IMF attractions or whatever have you between the molecules, that is going to get broken during our phase change and use that absorbed energy until we become a gas. And we keep absorbing energy. Theoretically, like way up here, we could have another phase change toward a plasma, but we don't need to worry about that in this class. Whoops. In terms of what attractive forces are breaking specifically, it really depends on the type of molecule that you're looking for. So if you have a molecular covalent substance, and again, that's a covalent substance that has individual discrete molecules, that means that when you do a phase change, intermolecular forces, or IMFs, are breaking. So in this picture over here, which represents water, the intermolecular forces that would break would be here, these little dotted lines, because as we know, intermolecular forces are represented by dotted lines generally. In the case of water, the intermolecular force that's happening is hydrogen bonding. And so to melt water, we have to break a hydrogen bond. Yes, it's not going to be every single hydrogen bond that exists because, again, in liquid phase, water can still hydrogen bond with itself, but it's not as intense as in solid phase. Then if we were to vaporize that water, the hydrogen bonds would break entirely, so on and so forth. Depending on the molecule you're looking at, the intermolecular force that's breaking could be London dispersion forces or dipole-dipole forces. Again, it depends on the molecule, but you should be able to identify that by this point because we have talked about these intermolecular forces already. However, if your substance is not a molecular covalent substance, let's say it's a network covalent or it's an ionic substance, we're not breaking intermolecular forces. Now we're breaking intramolecular forces, because the special thing about network covalents and ionics is that that big lattice structure is all one molecule. So let's say I was breaking or melting a diamond, like in this top picture, that would mean I'd have to break covalent bonds, right? Because in a diamond, in a network covalent substance, every atom is covalently bonded to every atom around it. So to melt it, it requires a crap ton of energy. And so we need to break one of the strongest bonds that exists, a covalent bond. If you're looking at an ionically bonded substance like salt, NaCl down here, we're still breaking an actual bond. We're breaking an ionic bond between the sodium and the chlorine ions. And so again, that's an intramolecular force, not an intermolecular force. If you have any questions about this, please talk to me in class.